All right, this is Pre-Calculus B, Unit 4, Lesson 1, Polar Coordinates. We approach mathematics a little bit differently. So far we've been graphing things in rectangular coordinates, an x and a y-axis called Cartesian coordinates. Were named after the French mathematician René Descartes. I never put Descartes before the horse, you know. X and y coordinates are one way to look at coordinates, but actually in many cases it's more convenient to talk about direction and distance. Let's say, for example, you're in a military aircraft or you're on a ship in the ocean, and you want to know, you've got an aircraft approaching your ship, right? You want to know if it's an enemy or if it's a friend. You want to know its position, right? Well, its position relative to your position means all the world. So what direction should we look, and how far out is the enemy aircraft? That would be the most vital information. Rather than x and y coordinates, we include direction and distance. So distance first, and direction second. We indicate that in polar coordinates as r, comma, theta. R is we think of r for radius of a circle, right? R, theta is distance. R is distance, and theta is direction. Now, theta can be expressed in either degrees or radians, and degrees are fairly straightforward. So we always measure things from the positive x-axis. So let's say I want to graph the point. Let's say I want to graph the point. Let's go with green here. Let's say I want to graph the point 3, comma, 30 degrees. Okay, 3, comma, 30 degrees. That would be at a distance of 3 from 30 degrees. And when I graph, actually, I look for the angle first, usually, myself. Now, this graph paper is set up in increments where this is 45, and those are thirds. Thirds of 45 are 15 degrees, so 15, 30, 45, 60, 75, 90, right? So let's go ahead and mark those angles. So 0 degrees, 15 degrees, 30 degrees, 45 degrees, or multiples of pi over 12 if you're talking radians, 60 degrees, and 75 degrees, and 90 degrees. Okay, so 30 degrees, look at the 30-degree ray and go out from the pole, this is called the pole, 3 units. 3 units along the 30-degree axis. 1, 2, 3. Okay, where this is 1, this is 2, 3, 4, 5, 6, 7, 8. So that's that coordinate right there. So we would indicate this as 3, comma, 30 degrees. Okay. Now, what's interesting about polar coordinates is that there are multiple ways to express the same point. For example, what if instead of stopping at 30 degrees, I went all the way down to 180 plus 30, right? 180 plus 30, or this would be 100 or 210 degrees. 210 degrees, but I made the distance -3. So this is -3, comma, 210 degrees. What that means is we go down to the direction vector for 210 degrees, and we face in the opposite direction, negative direction. So -3, comma, 210 degrees is also the same, 210 degrees is also the same point, right? Not only that, we can talk about negative direction. Negative direction, going clockwise is negative. So I could go around this way and end up at the 30-degree vector. So that corresponds to an angle of 360 less 30, negative 330, negative 330 degrees, and still a distance of 3. Okay, so we can express these in numerous ways, all right? But the idea here is that positive angles go counterclockwise. That's one of the big ideas. Positive angles go counterclockwise from the x-axis, and positive directions proceed outward from the pole. Negative directions proceed in the opposite direction, 180 degrees polar. All right. Now, most of the exercises here in this unit are going to be about converting between rectangular and polar coordinates. So let's convert this into rectangular coordinates. Okay. So what I do to do that is I think in terms of this right triangle. Okay. This is 30 degrees. And this is a radius of 3. So we know from our trig relationships that the opposite over the hypotenuse is sine, and the adjacent over the hypotenuse is cosine. So we use basically this, that the height of this triangle, is 3 sine 30. Sine gives you the height of the triangle, 3 sine 30. And the width is 3 cosine 30. Okay? So in rectangular coordinates, this is the same as the rectangular coordinates 3 cosine 30, 3 sine 30. Okay? And that's given by this formula, these formulas. X equals r cosine 30. Y equals r sine 30. But realize what you're doing is you're just solving for the height and the width of this right triangle. Okay, if you keep that in mind, it'll make much more sense. Okay, so use r sine theta and r cosine theta to r sine theta and r cosine theta to convert between polar and rectangular coordinates. But what about going the other direction? Let's say I've got the rectangular coordinates. 5, 7. Okay? So in rectangular coordinates, what we're looking at is a rectangular graph. 5 to the right, 2, 4, 5. And 2, 4, 6, 7 up. So 5, 7. Again, consider the right triangle here, formed right here. And what we're after in this case is we need the radius, we need the distance from the pole, from the origin, 0, 0, and we need the angle. Okay? We need the angle. So we need the radius and the angle. Now the radius is really fairly straightforward to find. I know the height of this triangle is 7 and the width is 5. So the radius by the Pythagorean theorem is 5 squared plus 7 squared square root. You can think distance formula or Pythagorean theorem. 25 plus 49 is root 74. Okay, so that's the radius. And likewise, the angle. Now to find the angle, I'm going to use the tangent ratio. Let's call this angle theta. Tan theta equals 7/5. So theta is arctangent, tan with a little -1, or ARCTAN in Desmos, of 7/5. Okay, now do realize that arctangent has some domain restrictions, so you always have to calculate the angle based on the context in which you are working. Okay. And so there we have it. So in polar coordinates, 5, 7 in rectangular coordinates converted to r theta is square root 74 and arctangent of 7/5. Okay. Now I do want to spend a little bit of time showing this to you in Desmos as well. Okay. So Desmos does have the ability to bring up polar coordinates. When you click on the wrench tool, it's one of the grid options here. You can go with polar or rectangular or polar. Okay. And now, unfortunately, you can't put polar coordinates in Desmos. It interprets them as rectangular. So if I do 5, 7, it's going to graph it. It's going to graph it just like rectangular coordinates, right? So if I switch between rectangular and polar, it doesn't change, right? That's 5, 7. That's 5, 7. And so the way to graph polar coordinates in Desmos is you have to use the r cosine theta, r sine theta. Okay. So let's let a equal. We had r was 3, and theta was 30, right? And make sure you know what measurements you're using, whether it's radians or degrees. Okay. And we're going to graph r cosine, a cosine b, comma, a sine b. Okay, and now you'll notice that corresponds to 3, right? And I can vary. Let's let a, which is r, be from -6 to 6. Okay, and let's let b be from 0 or -360 to 360. Okay. All right. So as r gets bigger, it gets further away. As r goes negative, it gets to 0 when it's 0, and then it goes negative, goes the opposite direction. Okay. When b, which is theta, changes, it travels around the pole, right? So we can kind of create a little bit of a polar graph this way. This would correspond to the plot 2.46 comma 30, right? And 30 degrees, 2.46 radius. All right, so that's how you handle it in Desmos.